So in this video, I wanted to look at the first problem from the practice exam, which involves applying the triangle rule in order to determine a resultant force. So this will be something that you're asked to do on the first exam. And the reason is it really emphasizes the power of the linear algebra-based techniques that we use for adding vectors, both after we covered this concept originally, along with throughout the remainder of the course. Namely, if we break vectors into rectangular components, we can simply add the components and avoid the natural geometric approach that vectors technically add by. So in order to apply the triangle rule, remember that you have to arrange the two vectors that you're trying to add in what is known as tip to tail fashion. I chose to place the actual tail of Q onto the tip of P. And when I do this, I want to incorporate whatever magnitude information I'm given about P and Q in order to draw this to scale. I just assumed that P was a little bit longer in Q. I actually didn't even copy the information that was given in the particular practice problem, since those quantities are obviously going to change. However, in addition to making sure that we accommodate the magnitude in the side lengths of the triangle that we draw, we also want to make sure that we incorporate whatever geometric information we're given into the triangle as well. So if you notice, P is actually inclined from the horizontal at 45 degrees. We won't use that information directly until a little bit later, and we'll actually use it up here. However, when I actually place Q in a tip to tail fashion with P, remember that Q is elevated from the horizontal by 30 degrees. How can we actually determine the total interior angle of this triangle? Well, we know that the portion from the horizontal up to Q is 30 degrees, and we know that from the line of action of P all the way extended to the line of action outside of the triangle is 180 degrees. So if we know that it is 45 degrees from the horizontal to the line of action of P, then the remainder of this angle must be 135, because if I go from one line to the other, that is 180. So technically, the interior angle of this triangle is just 135 plus 30, which is 165 degrees. How can we use that information in order to solve for the quantities that we don't know? Well, if we're given a magnitude of P and a magnitude of Q, which we are at this point, we have side angle side information, and we can solve for the other side length by using the law of cosines, which hopefully you remember from the actual lecture example that we did like this. So the square of that side length, which is going to be, of course, in this case, we're assuming that the side lengths are proportional to the actual magnitude of the force, is going to be equal to the square of the sum of the squares of the other two side lengths minus 2 times the magnitude of P times the magnitude of Q times the cosine of that interior angle that we just determined. Now, once we have this side length, we're in a much better position with respect to ease of computation because we can use the law of sines. Now, what do we actually need to determine? We know all three side lengths. We know this interior angle. We want to get this small little interior angle of the triangle here that we've marked by alpha, because that will allow us to determine the conventional angle by which we describe the direction of R. So how do we get alpha? Well, we know that the sine of alpha divided by the matching side length, which is going to be Q, is equal to the sine of this interior angle divided by the side length of the resultant, which we just determined in the prior step. Once we solve for alpha by isolating sine of alpha and then taking an inverse sine, we can determine the angle of the resultant by simply noting that the entire angle from the horizontal to P is 45 degrees. That can be written as the angle of the resultant plus that alpha angle that we just solved for. So in order to solve for the angle of the resultant, we simply take 45 degrees and we subtract away alpha.